Today, we are going to containerize a .NET Core application along with a SQL Server database. In this .NET Docker tutorial, I am going to take you step by step through the process. No previous Docker experience required. We'll cover all of the essentials: containers, images, Dockerfiles, Docker Hub, and Docker Compose. By the end of this tutorial, you'll have a working setup that is fast, portable, and production ready. Here's our plan for today. We're going to create two separate containers, one for our .NET Core application, the other for our SQL Server database. To create our .NET app container, we'll build a custom image using a Dockerfile. For our database, we'll save time by pulling a ready-made SQL Server image directly from Docker Hub. Finally, we'll use Docker Compose to run and connect both containers with a single command. If any of these terms are new to you, don't worry. I'll explain every concept in simple terms, breaking it down step by step so that you can follow along. But before we get into the what, let's quickly cover the why. Why should we use containers? It's consistent and reproducible. You'll get the exact same .NET app and SQL Server setup on every machine and every environment. It's a fast setup. A new developer can join your team, run one command, Docker Compose up, and have the entire application stack running in minutes. It's portable, so your .NET Docker setup will run the same regardless of whether it's on Windows, Mac, Linux, or deployed to the cloud. It also simplifies deployments. The container you test on your machine is the exact same one that goes to production. It also offers easy data management. You can quickly create a database with the right schema and data, and just as easily tear it down and start over again. It also makes your applications scalable and disposable. You can run more copies of your application when busy and shut them down when not needed. Now that we know why we should use containers, let's explain the core concepts. So Docker is a tool that allows you to run applications inside isolated environments called containers. A container is similar to a virtual machine. It has its own operating system, but unlike a virtual machine, a container doesn't simulate the entire computer. Instead, it's a stripped down sandbox environment that runs only what you absolutely need to run. This makes it much faster and lightweight compared to a virtual machine. You can think of a container somewhat like an apartment in a building. It has its own private space, but it shares the building's main infrastructure, like its plumbing and electricity. Images, you can think of an image like a blueprint for your container. It defines what software, libraries, and settings should be inside the container. For example, in our .NET Docker image, we'll include the .NET runtime so our app can run. When you run an image, it becomes a container, a live instance of that blueprint. Quite similar to how in .NET C#, an object is an instance of a class. The class is the blueprint, the object is the instance. Then we have Dockerfiles. So a Dockerfile is a set of instructions that tells Docker how to build an image. It runs commands like installing software, copying files, and setting up your app environment. So here's the flow with a little bit of an analogy. We write the Dockerfile, which is our recipe. We run the Docker build command, which follows that recipe to create a pizza. This is our image. Finally, we run the Docker run command, which bakes the pizza and serves it. Ready to eat pizza? That's our container. Now let's take a quick look at the application we're going to containerize. It's a simple .NET app providing basic CRUD functionality for a library of books. It doesn't matter whether your app is an MVC app, a Blazor app, a set of minimal APIs, or any other type of .NET app. And it doesn't matter what version of .NET you're running, the process is going to be the same. This application that I'm showcasing here persists data to a SQL Server database. Here's the database context class. This checks if the database exists when the application starts up, and if it doesn't, it creates it. For a demo, this is fine, but I just want to highlight that this is a bad practice in a real production environment. A better approach for a production application would be to use a database migration tool. That would probably require a video in its own right, so we'll park that for now and cover that in a future video. Now that you've seen the app, let's containerize it. First, we're going to want to make sure that we have Docker Desktop installed. If you're prompted to, do also install Windows Subsystem for Linux, WSL for short. This lets you run Linux containers on a Windows machine. Docker relies on the Linux kernel, so even on Windows, most containers will be running Linux under the hood. With Docker installed, now we'll add a Dockerfile to our .NET application. We'll let our IDE scaffold the Dockerfile. I'll show you how to do this with both Visual Studio and Rider. In Visual Studio, we right-click on our project, go Add Docker Desktop. We'll leave all the scaffolding options as their defaults and click OK. In Rider, we right-click on the project and click Add Dockerfile. Whether you use Rider or Visual Studio, doesn't matter. The file that's generated will be the same. Before we dive into the Dockerfile, you might notice that the IDE created another file for us, a dockerignore file. Don't overlook this file. It is the unsung hero of building efficient and scalable containers. It's similar to a dockerignore file if you've used Git. It tells Docker which files and folders to ignore when building an image. The IDE here has pre-filled our dockerignore file with common .NET folders we want to exclude, such as the bin and object folder. So why is this important? One, it's going to make your builds faster because Docker isn't going to waste time copying temporary build artifacts and other unnecessary files. Two, it creates smaller images. By leaving out junk files, the final image is going to be leaner and more efficient. Three, it improves security. It prevents you from accidentally copying sensitive files such as local configuration or user settings into your image where they could later be exposed. The IDE did the heavy lifting for us here, but it's crucial that you know why this file exists and why it's best practice to have one. Okay, now let's go back to our Dockerfile and understand what it's doing. The Dockerfile contains the steps necessary to containerize our .NET application. It uses a technique called multi-stage builds. This separates the steps of building, publishing, and running the app. This makes the final image smaller and more secure. Here's the high-level flow. The base stage sets up the minimal runtime environment. The build stage compiles our source code. The publish stage creates an optimized, ready-to-run package. The final stage copies only the published app into the clean base image. This multi-stage build pattern ensures that each stage has a specific job, e.g., restores dependencies, builds the app, publishes it, runs it, can reuse work done in other stages, helps keep the final image smaller and cleaner. Now let's dive a little deeper and understand this file line by line. In this stage, we define the base runtime environment. This line starts a new build stage from a base image. The base image here comes from Microsoft's official image for .NET 9. It contains the .NET 9 ASP.NET runtime. This is the minimum environment that we need to run the app, not build it. The as base gives the image a name of base that we can refer to later. This line tells Docker to run the container as a non-root user. In Linux, which most Docker containers are based on, there's a special user called root. This is the super user, the user that has full control over everything. Running as root means the process can access or modify any file, change system settings, and therefore break things and be exploited by attackers. By default, containers run as root, which is convenient but not very secure. Running your app as a non-root user limits its permissions inside the container, reduces the damage if a vulnerability is exploited, and is therefore considered best practice for security. This line switches the user specified by the environment variable app UID. So the actual user ID can be specified outside of the Dockerfile, giving you more flexibility. If this variable isn't set, when building the image, the container might default to root, which isn't recommended. This line here sets the working directory inside the container to the app directory. All commands that follow from this point will be ran from that directory. These lines tell Docker that the app will use ports 8080 and 8081. These ports are very commonly used for web apps during development. While the expose keyword is used here, these lines don't actually expose ports to the outside world. They just document which ports the app is listening on inside the container. Think of the expose keyword as a label on the container. It just says the application inside me is listening on port 8080 and 8081. It's just documentation. It does not open ports to the outside world. Okay, that's all of the lines in our base runtime environment stage. As a reminder, all this stage is doing is setting up the runtime environment that our app will later use to run on. Now let's look at the build stage. In this stage, we compile our code. Just like the previous stage, we start with a base image. This time, the base image is going to be the .NET 9 software development kit. If you're using a different version of .NET, the SDK listed here should match your application's .NET version. When you generated the Dockerfile using your IDE, the IDE would have pre-populated with the correct SDK, so you shouldn't need to change this. The reason we need a .NET SDK is to allow us to compile our code. The as build part here gives the image a name of build so we can refer to it later. This line defines a build time variable called build configuration. ARG stands for build argument. It's like a temporary variable that only exists whilst the image is being built. When building .NET apps, you can choose different configurations like debug or release. Release produces optimized code, strips out debug information, and is intended for production use. Next, we'll change the working directory to source. This is where we're going to place the application's source code to build it. Then we copy the application's CS_proj file into the container's source folder. And then we run the .NET restore command. This downloads our app's dependencies. This line copies everything in your project folder on your machine into the container's source folder. You might be asking yourself here, why did we copy just the CS_proj file, run a .NET restore, and then go and copy everything else? Why not just copy everything straight off? Well, this is a caching trick. Dependencies don't change very often, but your source code does. So if you copy your CS_proj first and it hasn't changed, Docker can skip running .NET restore. It just uses the cached dependencies. The next line here ensures we're still in the right working directory. It's actually a little redundant here since we already know we're in the source folder, so if we want to, we can choose to remove this line. The final step in this stage, we build the app using the .NET build command. The -c flag here stands for configuration. This uses the value for the build configuration environment variable, which will default to release unless you choose to override it. In release mode, .NET applications are optimized for performance and smaller file sizes, which is perfect for production. The -o flag stands for output directory, and it specifies where the build files will go. /app/build is just a temporary folder inside of the container where our compiled code will be stored for the next step. Okay, that's the build stage covered. When this stage runs, we will have compiled our application. Next on to the publish stage. In this stage, we package our .NET app. This line starts a new stage called publish, and it uses the build stage we defined previously as its starting point. This line defines a build time variable called build configuration and sets its default value to release. This will let you control whether the application is built in debug mode for development or release mode for production. This line publishes your .NET app. The .NET publish command creates a self-contained version of the app ready to run on a server. It includes the compiled code and the necessary runtime files. Publish is the final packaging step before shipping. It bundles everything that the application needs to run, but leaves out all of the build tools. The -c flag sets the build configuration using the build configuration variable. This affects optimization. Release makes your application smaller and faster. The -o flag tells .NET to put the published output into the /app/publish folder inside of the container. This folder will later be copied to the final image. The -p use app host equals false disables the generation of a platform-specific executable file. This results in a simpler, more portable app that you can run using the .NET command. Upon completion of this stage, we will have published the app. Now on to the final stage. This part of the Dockerfile creates the final production-ready image, the one that will actually run your app when you deploy it. It pulls in just the published output from the previous step, places it in the right folder, and sets the command to start the app. As with each of the previous stages, this line starts a new stage, and we'll name it Final. It uses the previously defined base image. This image contains just the published app and the minimal required .NET runtime. We change our working directory to /app. This is where the app will live and run inside the container. This line copies the published app files from the publish stage into the current app folder. The -- from equals published means go grab the files from the stage named publish. The /app/publish directory is the folder that we previously stored our published output in. And the dot here means copy these files into the current directory, so the app directory. This ensures only clean, ready to run files are included in our final image. No source code, no build tools, nothing extra. Finally, we have the entry point command. This defines the command that is executed when the container starts. It tells Docker, when you run this image, launch the app by running this DLL using the .NET command. This is what actually starts the web app. Okay, so that's the final line of our Dockerfile. But before we move on, let's take a moment to recap what we've done so far. So we've created a multi-stage Dockerfile that will containerize our .NET application efficiently. Here's how that process flows. We have our base stage that sets up the environment required to run the application, so the runtime only, no build tools. We have our build stage. This installs our dependencies and compiles the application. Then we have our publish stage, which packages the app by publishing it to a clean folder. And then in our final stage, we create a minimal production-ready image using only the published files and runtime. This multi-stage process ensures our Docker image is small, secure, and production-ready. Now let's build our Docker image and run the container. Let's open the terminal in the directory that contains our Dockerfile, and let's run the command docker build -t bookapp dot. The -t flag allows us to tag our image with a name of bookapp, and the dot is just stating the current directory. Once that image has been built, let's run our container. We'll use the command docker run -p 8080:8080 bookapp. Let's break down what that command's doing. So the -p 8080:8080 is saying map port 8080 inside of the container to port 8080 on our actual machine. Remember previously in our Dockerfile where we used the keyword expose and we said expose 8080, and we talked about how we weren't really exposing the port to the outside world. We were just saying that the app was listening on that port. Well, this -p flag, what we're now doing is actually exposing that port. So inside the container, port 8080 is now exposed to the outside world, again on port 8080. And the final part of this command where we specify bookapp is the name of the image we built earlier. Now let's go and browse and go to localhost port 8080. Okay, so we're getting a SQL error here, and that's to be expected. Our app is now running inside a container, but SQL Server is not. Our app is trying to connect to a SQL Server database that doesn't exist. This is the perfect moment to introduce the next tool in our Docker toolkit, Docker Compose. Docker Compose lets us spin up multiple containers at once and wire them all together. So in our case, we will tell Compose to spin up our .NET app container using the Dockerfile that we just wrote. For our SQL Server container though, we don't need to build this ourselves. Microsoft provides an official SQL Server image that we can pull down from Docker Hub. Docker Hub is an online service for sharing Docker images. It's like GitHub, but rather than being a code repository, it's an image repository. Once both containers are running, Compose will also create a private network so that our .NET app can talk to the SQL Server database using its container name rather than us needing to specify an IP address. That means no manual connection setup, no fiddling with IP addresses. Compose handles it all for us gracefully. The final concept that I just want to introduce here is something called a volume. Whenever you stop or delete a container, everything inside that container is gone. What a volume allows us to do is to persist data even after a container has been removed. Okay, so now let's go and set up our Docker Compose. Let's create a new file in the root of our project next to our Docker file called docker-compose.yaml. This is where we will define both our containers, our .NET app and our SQL Server, and describe how they should run together. So a Docker Compose file is just YAML, a structured text format that Docker Compose reads to know what images to use, what ports to expose, what environment variables to set, and how each of our containers should connect to each other. For speed, I'm just going to paste a version of this that I prepared earlier, but don't worry, we'll go through this line by line just like we did with the Dockerfile. I'll also just mention that all of the code we're showcasing today is available for you to go and take a look at. Just go check the description below. Before we start breaking down this Docker Compose file, if you're finding this content useful, then click the like button. It only costs you a click, but it's huge for the channel. Okay, let's move on and break down this Docker Compose file. First, we'll define what version of Docker Compose we are using. Then we'll define our services. These are the containers that we want to run. Our first service is our web service. Build dot tells it to build the image using the Dockerfile in the current directory. Ports maps port 8080 inside the container to port 8080 on our machine, and depends on ensures that our database container is running before our web app. Next up is the environment block for our web app. This is where we pass in configurations such as connection strings into our .NET application. And this single line right here is packed with two of the most important concepts within our Docker Compose. So let's break this down carefully. First, the magic of networking. Look at this part right here where we say server equals DB. Where did that DB come from? It's not localhost or an IP address. This is the first piece of the Docker Compose magic. The name DB directly matches the name of our other service that we define below, our SQL Server database. Docker Compose automatically creates a private virtual network for our containers. Inside this private network, our containers can securely find and talk to each other using just their service names. This is called service discovery. It means we don't have to worry about hard coding IP addresses. And our .NET web app will be able to reliably connect to our SQL Server database. It's clean, it's simple, it's incredibly powerful. Now for the second critical lesson of this line. As we continue reading, we see this, password equals your password 123. And this brings us to a huge best practice that we must follow. Putting a password or any kind of secret into this file is a huge security risk. If we were to commit this Docker Compose file as we see it now to source control, we would have just leaked our database password. So let's fix that straight away. To do that, we'll use an environment file. Let's create a new file in the root of our project called .env. Docker Compose will automatically look for this file to load environment variables. This file is for our local secrets, so it should never be committed to source control. In fact, you should add this to your dockerignore file to ensure that it is never accidentally committed to source control. Inside our .env file, let's create our password variable. Great. Now we can go back to our Docker Compose and replace the hard-coded password with a reference to that variable. The syntax here is $, open and close curly brackets, and inside that, the variable name. With that quick change, our configuration is now secure. Our password is now safely secure in our local environment file and completely separate from our shareable configuration. Next, we'll define our DB service, and here things are a little bit different. Image tells Docker to use the official Microsoft SQL Server 2022 image from Docker Hub. What we're saying here is don't build anything. Instead, go and pull the image that Microsoft has built and provided from Docker Hub. This is a really key concept. You should always use official pre-built images for common software like databases, caches, message brokers, etc. In environment, we accept the license and we set a sysadmin password. And then ports, we map SQL Server port 1433 inside the container to port 1433 on our machine. Now let's use Docker Compose to spin up both of our containers. We can do this from the terminal using the command docker compose up -- build. This single command will build the web image using our Dockerfile that we wrote previously. It will go and pull the SQL Server image from Docker Hub if it's not already on our machine. It creates a private network for both of those services to communicate with each other, and it starts both of those containers. The -- build flag ensures that the Dockerfile instructions are rerun every time. Using the build flag ensures that the container that you run includes any code and config changes you might have made. Now let's test it by going to localhost 8080 again. Our app should load this time successfully. There we are. The app is now running and we can tell that it's connected to our SQL Server database. One small problem we have here is anytime we restart these containers, we're going to lose any data we try to persist. If you want to be able to keep database data between runs, what you'll need is something called a volume. Let's see how to set that up. Here we specify a volume MS SQL data. This maps the SQL Server data folder inside of the container to a named volume on your local machine. That way, even if you delete and recreate the container, your data persists. And there you have it. We have just containerized a .NET Core application along with a SQL Server database. You can now give this project to any developer, and with one command, docker compose up, they will have the full stack running in just a couple of minutes. If you found this video helpful, then please do hit like and subscribe for more content. You've been watching Mace Labs. Thanks for watching. See you next time.